In this lecture, we will apply Cauchy's integral formula to derive some estimate, which are which is used in not only in complex analysis but also in harmonic analysis, PDE, and etc. So we first we first define the kernel function. What is a kernel function? Suppose you have function k and in some variable z, complex variable z, and we define operation f convolution k z to be f Cauchy times k Cauchy minus z d Cauchy. Here my notion is very sloppy, but the key point is the kernel function is always used to do convolution, to do some twisted integral with some other functions f. For example, you can do this for all f for all holomorphic. For different setting, you might have different kernel functions, and you have different operations on function spaces. In other words, which function f can be operated by the kernel function k. Okay. Then in this language, we can just interpret the Cauchy integral formula in this form. Otherwise, in other words, what is Cauchy formula? You just do integration, do convolution with a function 1 over Cauchy or 1 over z. And you have this. So all the special property comes from the function 1 over z. So remark, 1 over z is very important. So for example, from this one, you can see the kernel just reproduce your function f. When you throw f into the kernel function 1 over 2 pi I times 1 over Cauchy, then you just get back the original function. You reproduce it. This is very special. And the speciality of this comes from the fact that 1 over Cauchy is holomorphic outside the origin. This is first fact, it's holomorphic. Second fact is, and the most important fact is, it's singular. Okay, it prescribes some singularity at the origin. So, what is singularity? Is important in mathematics. In general, singularity is bad. You don't know how to control it. People spend a lot of time to resolve the singularities. But some subtle singularity can give you some unexpected good properties. So I want to say all the nice stories, large portion of the nice story comes from the singularity. And if you know a little bit physics or whatever, so it's very similar to Green's function. And you have retarded Green's function, which is also some convolution of 1 over omega, whatever, p omega, blah blah. But it's more subtle. And if you Feynman's Green's function, it's another story. You need to truncate it. You need to time ordering the Green's function. So it's partially 1 over omega and partially some other thing. You have some artificial truncation. And when we study the residual theorem, probably we will talk about this. It's from mathematical point of view, just application of residual theorem and some decay estimate. But in physics, of course, you do have some other explanation. Okay, but here a Green's function, actually Green's function in 3D is same as Newtonian potential. And more in general, in higher dimensional, you have the singular integral. So this is called the Calderon-Zygmunt theorem, which is a root for the whole subject of function analysis. And its lower dimensional part is called Hilbert transformation. But what we study actually is simpler, much simpler than the harmonic analysis or singular integral, because what we study, by that I mean the Cauchy's integral formula, is simpler, much simpler, because in the integration we don't have any singularity. This is well defined. Riemann integral. You do have a smooth function and a nice boundary, but of course you need to assume that Z is inside the domain. Okay, but for Green's function, usually you do have the singularity. For example, a good question is, what if Z is on the boundary? Then this is not well defined. The integral is not well defined. So I can draw a picture. So suppose this is your boundary. If your point Z is here, then how do you define the integral? So you might just say, okay, then I stop here. I don't get too close to the singularity. This is one way to interpret this. The second way is, okay, I just do some detour from inside. Or you might see, why not do detour outside? Okay, so all these give you different values. And actually first one corresponding to the Hilbert transformation. The second one just give you 0. Third one gives you the residue. But for the singular integral part, the Green's function, you always integrate, your integration always have singularities. So that's a more technical part. We will not discuss in detail, I think, in most this course. All I want to say is the specialarity of the Cauchy integral formula comes from the singularity. Okay, next we apply the Cauchy integral formula to do some estimate. So first one is Cauchy's inequality. So suppose Fz is holomorphic on the disk, then we can estimate the derivative of any order at the origin. The proof is easy. We just write down the Cauchy integral formula for the disk with z equals origin. And then you take the norm. You have, this will be less than n factorial divided by 2 pi, and then integration over f Cauchy divided by r to the n plus 1's power. And then you can further bound the function by the supremum of the function on the boundary times 1 over r to n plus 1's power times, then what you have is length of the contour. So this is actually 2 pi r, just length of the circle. So finally, you have r to n's power supremum, f Cauchy minus a equals r. And a good application of Liouville theorem. So a bounded holomorphic function on the whole plane must be constant. Prove. Suppose A is a positive real number such that the holomorphic function f is bounded by A on the complex plane. Then, for any point A in C and r greater than 0, we have the derivative of f at the point A is less than or equal to 1 over R supremum Z minus A equals R Fz. You have this. And immediately let R goes to party infinity. What do we have? The left-hand side of this, of the yellow inequality, doesn't depend on R, but right-hand side does depend on R. And we have f derivative, the norm of f derivative at point A is less than or equal to 0. In other words, the derivative of f at point A is 0. But since A is arbitrary, then what does that tell you? That tells you f z is a constant function. You just do the line integral to get a primitive of f prime. So f is f prime Cauchy d Cauchy along some loop up to some constant, therefore it's 0 plus some constant. Okay, then you are done. The proof is sharp, but then it contains a lot of meaning. Actually, this theorem is a very special case, but important case of the Picard's bigger theorem or small theorem. And later on, people develop a full machinery called the Navier-Stokes theorem or value distribution. Basically, this says a holomorphic function on the whole complex, defined on the whole complex plane, takes all the complex values except at most 3 points. Yeah, probably we will discuss this later. And as I mentioned, there's a great complex analysis called Alphos. Who introduced a geometric interpretation of this by characterize this property by negative curvature or positive curvature. Or zero curvature. So negative curvature, later on we will introduce just the most basic domain. Disk is negative curved. And the positive curve is just a sphere. We will show later that on sphere you do have positive curve. See, actually this is more related to algebra geometry, and I do have some research work on this. It's very interesting. And then zero curvature, just a complex plane. C. So this is called CP1. This is called disk. And then the theorem actually tells you C cannot map into cannot holomorphically map into disk D. But of course, D can map into C. Okay, then from algebra geometry, CP1 it also cannot map into what's called map into D, and CP1 cannot map into C. Except trivially. Non-trivial. Trivially means just a point. So if you want to get some pattern out of these properties, then you might conclude that, just as what Alphas did, the curvature. So suppose if you have a holomorphic map from omega to omega bar, then curvature cannot decrease. It can be the same, but cannot decrease strictly. This is a geometric interpretation, and then people introduce Kobayashi hyperbolicity, and which is a higher dimensional generalization of this. Okay, all I want to say is, although the theorem is very simple, but later on people develop a very complicated theorem on this. Yeah, but I still love the original one. It's very clean, and the proof is very short. Yeah, if you have interest, we can have a talk, and I will introduce some paper or textbook to you, or you can just check on the Wikipedia. Okay, next let's give another application, which is called fundamental theorem or algebra. It's not calculus, it's algebra. It's said that Gauss, all his life, developed a lot of different proofs of the fundamental theorem or algebra, but I guess all the proofs should rely on analysis. So although the fundamental theorem or algebra, but it's actually a property of analysis. So suppose now we give a proof based on complex analysis. Suppose Pn is a polynomial of degree n greater than 1 in variable z and with complex coefficient. Then the fundamental theorem of algebra states that you have a factorization, or you have n roots multiplicity counted for some non-zero complex number C and n complex roots A1, AN. It's clear by induction it suffices to prove that the polynomial of degree n has one solution certain complex number, z. Then you can just factor it and do the induction, prove the whole factorization. Okay, suppose the contrary, then 1 over p and z is holomorphic function on C. So why this is true? This is a crucial property we will use. And then we want to estimate the norm of Pn. So we write out its coefficient. In particular, the leading coefficient P0 is non-vanishing. Then P and Z norm is given by z to nth power P0 plus P1 divided by Z plus Bn divided by Zn. Okay, it's clear if the norm of Z is greater than it's very large, then the blue part will be relatively smaller than B0. And here I choose this weird quantity just backwards from what I need later. Take this, then P and Z is greater than Z to nth power, and B0 minus B1 plus Bn divided by Z norm. This is greater than Zn times B0 divided by 2. And for all Z greater than the above quantity. Okay, therefore 1 over P and Z, the norm is less than or equal to 1 over Z to nth power times 2 divided by B0 for all Z greater than this part. So if you draw a picture, what do you have? We showed that outside a disk with this radius, P and Z is bounded. And since F is holomorphic, 1 over Pn is holomorphic, then inside the disk, it's also bounded because the disk is a compact set. Therefore, we conclude, 1 over P and Z is bounded on C by Liouville theorem. One over P and Z is a constant. P and Z is a constant, which is a contradiction, because we assume that Pn is a polynomial of degree at least 1. Okay, next we give another application, which is related more to the harmonic functions. It's called mean value properties. holomorphic functions as reformulation of Cauchy's integral formula for a point and a circle centered at a point. So let fz be a holomorphic function on z minus a less than r, and the radius and the real number small r is between 0 and capital R. Then Cauchy's integral formula fa 1 over 2 pi z minus a equals r fz z minus a dz yields. Okay, now we use the polar coordinates for z. Then we have f 1 over 2 pi I 0 to 2 pi dz fa plus I e I theta divided by r e I theta times r e I theta times I d theta. This is 1 over 2 pi from 0 to 2 pi fa plus r e I theta d theta. So if you draw a picture, you have a circle, no matter what radius it is, and then you integrate along the circle with respect to the angle theta. And do the average. You have the value of the function at the center. 1, 2. So here, actually, the 1 over 2 pi integration of some function d theta, just average. Because if you plug in some constant function, you just have the original function. For example, you plug in 1, then the answer is 1. Okay, and the remark is suppose you have a real function. U is a real function. U a equals 1 over 2 pi divided by, integration from 0 to pi u a plus r e I theta d theta for all a in omega, and a plus I e I theta also in omega. Then u is a harmonic function. Harmonic function means the Laplacian Laplacian u equals 0. Yeah, we will not talk about the details of the regularities or harmonic functions and whatever. Actually, here u can be assumed only to, for example, L2 integrable or L1 integrable. By Well's lemma, you can get the regularity of u. U is actually is smooth. Okay, C infinity smooth. It's analytic, real analytic. Okay, and so here the key property of the mean value theorem is that you choose the point A to be the center. If you shift A from center to some other point, then the weight will be different. But of course, you can write down that. So then that weight will be the Poisson kernel. We will study it later when we discuss the Hilbert transformation. And then immediately from the mean value property, we can introduce the maximum modulus principle as a consequence of mean value property of holomorphic functions. Oh, here, another remark is from this one, another definition for mean value property is given by the integration along the whole disk, dru x, y, dx, dy, 1 over the area of the disk. This is another kind of mean value property. And A is the center of dra. Okay, so the maximum modulus principle is that if F is holomorphic on a bounded, connected, open subset omega of C, then the supremum cannot achieve at any point A in omega. Here we don't assume any regularities of the boundary of omega unless Fz is a constant. So the proof, suppose supremum of Fz achieves at z0 in omega, then we can take a ball BRZ0 in omega and by the mean value property we have the following mean value property. You have MVP A plus EI theta D theta. Then you have FA less than or equal to 1 over 2 pi 0 to pi integration d theta less than 1 over 2 pi integration 2 pi supremum of f on omega d theta. So this is because the supremum is achieved at point oh sorry here so A is actually Z0. My bad notation. Okay, so it's 1 over 2 pi times 2 pi times FZ0. Therefore, all the inequality holds. Then, in particular, Fz is a constant. The norm of Fz is a constant for all z in omega. It's a step closer to what we want to prove, but still not exactly because because we want to know f without the absolute value, absolute simple, is a constant. So here we actually have two sub-statements. So first statement, this one. Second statement is if Fz achieved at the interior, in the interior, then it's a constant. Okay. So next we proceed as follows. If Fz0 is 0, then we have nothing to prove because then the norm is 0. Fz is 0 for all z in omega. It's a constant. Okay, otherwise, we consider the following integral. So on the one hand, we have 2 pi f fa plus rei theta d theta. Oh, 1 over 2 pi, sorry. Yeah, I should say this. Consider holomorphic function f inverse z0 fz. Then you apply mean value property again. Then you have this integral should be 1, which is the value of the function at the center. Okay, next. Next, since all the inequality holds, then what do we have? We have, let's denote this as I. So I is also equals to the integration 0 to pi f inverse z0 f z0 plus rei theta, you take also simple, value simple. Okay, now this greater than or equal to 0 from 2 pi real part gz d theta, sorry, g just the new holomorphic function we just defined, plus rei theta d theta, and this will be the real part 0 to pi g, sorry, f inverse z0 f z0 plus rei theta d theta. And since this is just 1, so this is 1. This is 1, so the real part is 1. Then what do you have? Then you immediately conclude that f inverse z0 f z0 plus rei theta equals real part of the same function. Okay, then in particular we have that fz is a constant for all z in omega. Okay, so I leave it to you why it must be a constant. Actually, you know, this function, this holomorphic function, has no imaginary part. Okay, then from there you can conclude this. Okay, next, we generalize the Cauchy's estimate to the disk version, which is called Schwarz lemma. As estimate for holomorphic functions near 0. So theorem: if fz is a holomorphic function on the unit disk with value less than 1 strictly, and the origin is mapped to the origin, then the norm of f is bounded by the norm of z, and the derivative at the origin is less than or equal to 1. Moreover, if the norm of f equals the norm of z for some z in the unit disk, or if the derivative, the norm of derivative equals 1, then f, the function f, holomorphic function, must be exponential e alpha times z for some alpha, for some real number alpha. In other words, f is a linear function So we consider function gz defined by fz divided by z, and so we click this is holomorphic function. We will show next time. When we discuss the zeros or holomorphic function, but basically, what you have is f has a power series expansion with lowest order is or order 1. Then g can be written down as power series an plus 1 z to nth power. So this is convergent in D. Now we transform the information of f to g, conclude that the norm of g is less than 1 for z in D. So here f prime at 0 gives the limit of gz when z goes to 0. And we use maximum modulus principle. Consider next we use maximum modulus principle. So consider gz on small disk z less than r with r less than 1. Then if z0 is in dr, we have gz0 less than or equal to supremum z on the boundary gz and this will be 1 over r. We plug in the value of f. So let r goes to 1 minus, we have gz0 norm is less than or equal to 1. Yeah, that's what we want for the first part, the inequality part. Then consider when the equality holds. If fz0 norm equals z0 for a certain z0 in D, then corresponding gz0, the norm is 1 by maximum modulus principle. Gz must be constant of modulus 1. Therefore, Gz is exponential I alpha. Similarly, if the derivative at the origin is 1, then we also have G0 is 1. Normal G0 is 1. we conclude the same thing. Okay, then we are done with the proof. Next time, probably we will discuss more on the geometrical intuition on this part.